everyone, and welcome back to Physics 2B. Today we are going to look at electric current, resistance, and Ohm's law. So let's get started with the idea of current. So current is the flow of charge, and it's represented by a capital I. So it's going to be the rate at which charge flows. So this is the equation to describe that motion. It is I is equal to delta Q, or the change in charge, divided by delta T, or the change in time. Okay, and here we can see this idea of current. So the current will travel, the charges will travel through some area here, some cross-sectional area, and so it's going to be the flow of those charges through that area. Okay, and here are the units. The units are coulomb per second, or amps. So this is amperes or amps. Okay, so this is the idea of electric current. Very similar to maybe you've heard of current flow of water. Okay, it's going to be something like that, but now we're looking at charges flowing. All right, so let's look at the direction real quick of the current. So the current is going to be in the same direction as electric fields. So here, okay, when we have positive charges, that those positive charges will be in the same direction as the electric field as well. Okay, now, so these are positive charges. Now we can look at negative charges down here. And as you can see, they will be flowing in the opposite direction to the electric field. So opposite to E field. Okay. And then the electric field again will be in the same direction as the current. Okay, the electric current. Okay, so let us look at an example real quick, example 20.1. What is the current involved when a truck battery sets in motion 720 coulombs of charge in 4 seconds while starting an engine? Okay, so we just found that current is equal to delta Q over delta T. Okay, so we can go ahead and plug these in. We have 720 coulombs of charge and 4 seconds, so 4.0 seconds. So we can plug that into our calculator. Nothing too crazy. We get 180 coulombs per second. So this is our current. Okay. Now to part B. How long does it take a 1 coulomb of charge to flow through a handheld calculator of 0.3 milliamps? This is milliamps. Is there 2 L's? I think so. I'm not positive. But this is times 10 to the negative 3, kind of like milligrams, okay? Or no, milli is times 10 to the, ooh, give me just a second here. Yeah, okay. Yeah. So I'm right. Okay, so milliamps is going to be times 10 to the negative 3 amps of current is flowing. So we have our charge Q, and we have our our current I. So we will go ahead and rearrange this equation to look like delta T, our time, equal to delta Q over I. Okay, this is hurting my eyes. Let me get out a black ink here. Okay, sorry about that. So let's go ahead and plug this in. We have our delta Q, which is 1 coulomb, and our current 0.300 times 10 to the negative third amps. Okay, so then we do that in our calculator. 1 divided by 0.3 times 10 to the negative 3, and we'll get, whoops, oh shoot, okay, we get about 3.33 times 10 to the third, and this is coulombs per amp or seconds. Okay, so this is the amount of time it takes for charge to flow through our calculator. We can also convert that. So let me see if I do by 60. This would be about 55 minutes. 1 coulomb of charge. Does that sound right? I believe so. Okay. So this is how you would find your current, your time, and then if we needed to find some sort of charge, if need to find charge, we would say delta Q is equal to I times delta T. Okay. All right, let's go ahead and move on here to Ohm's law. Now, George Simon Ohm was the first to demonstrate experimentally that current in a metal is directly proportional to the voltage that is applied to that metal. Okay, and so we can say I is proportional to V, so that's what this means, proportional. Okay, and we now know this as Ohm's law. It's viewed as a sort of cause and effect relationship where voltage is the cause and the current is the effect to that cause. Okay. Now, with that, there was also something else that came about, which is called resistance, or R, and that's the electric property that impedes current. Oops, where's my mouse? Okay, it impedes current, so it tries to stop it. Okay, this is similar to friction, such as air resistance or surface friction. Okay, this is trying to stop that current flow. Okay, so there's also a relationship between current and the inverse of resistance. So with those two things in mind, we came up with this equation here. I is equal to V divided by R. So current is equal to voltage over resistance. Okay, and there is the ooh, okay, this is these should be switched. Resistance has units of ohms, so you can draw them like that. They're kind of a funny little symbol there, but that is an ohm. Okay, so these should be switched here if I want to match this equation. Or we can say resistance is equal to voltage over current. Okay. All right, and so that relationship, I want to quickly show you guys in a simulation here. It's nothing fancy, but it just kind of shows you once you move one of the values of voltage or resistance, the current is going to change. So if I increase my voltage here, okay, my current is going to increase. You can see that increase here, okay? Now, if I do the same with resistance, increase my resistance, my current is going to lower, okay? Now, if I decrease the voltage, my current is going down, okay? If I decrease the resistance, my current will increase, okay? So looking at those relationships can kind of help you understand what this all means, okay? So this is also another form of Ohm's law. Voltage is equal to the current times the resistance. V equals IR, okay? So let's go back to our slideshow here. And where was I going to stop? Okay. Let's talk about a simple circuit. So this is going to include a single voltage source and a single resistor, like in this photo here, okay? This is going to include a closed path for current to flow, and it's going to be supplied by conductors like metal wires, okay? So we'll have metal wires going through, connecting one thing to another. And they will connect to terminals on a battery, okay? And that's what this is here. So the voltage will be applied, and this is typically like a battery, some sort of battery source, and that's what these parallel lines represent. The longer is the positive terminal, and then the smaller one is the negative terminal, okay? And then we also have a resistor here. That's what these like squiggly lines are. That's going to have any sort of resistance to the voltage source. So this is going to, like we just saw in that simulation, try to slow down that current or decrease the current, okay? And so we will hopefully be able to do this in class, and to show us. If not, we can do a simulation of this to show this relationship, okay? All right. So here is the last example in this section, and we are looking for the resistance of an automobile headlight through which 2.5 amps flows when 12 volts is applied to it. Okay, so we want to find the resistance again. So remember, resistance is equal to V over I. So resistance is equal to V over I, right? Or V equals IR. Remember we saw that in the simulation that I showed. So this formula will be, rearranged multiple times for us to find what we're looking for. Okay, so we'll be using this quite a bit. So we can go ahead and plug this in. We have a voltage of 12 volts and a current of 2.5 amps. Okay, so 12 divided by 2.5, 2.5, we get a resistance of 4.8 ohms. Again, that is an ohm, okay? All right, so I'm gonna pause here, and then when we come back, we'll continue our discussion with measuring voltage.